So we learned a little bit about sum and difference identities. I just mentioned the cosine. There is a similar one for sine, and there is another one for tangent. But thankfully, people don't push their luck with secant and cosecant and stuff like that. They can be created, but they don't have much use, and people don't pay much attention. So before we go any further on that direction, let's just back up a bit and do a little bit on the very basic identities we learned last time. You remember we had Pythagorean identities. We had, of course, some basic identities. The basic identities had what was it? Reciprocal, and then we had ratio, and then we had negative angle identities. Let's see if we can do some examples based on this and see how the simplification process goes on, and if we have digested these identities. So here's a question. Simplify. So that dreaded word, simplify cosine of x over 1 plus sine of x plus tangent of x. Simplify is more or less like try to see what you can do with this thing. Our expectation is that the end result of cleaning this up is going to be an expression that is going to be shorter than this. You know, as if chalk or digital chalk was expensive and we were trying to save on that. But of course, it's an issue of understanding an expression. If this expression, once it is simplified, everybody agrees on the final result being nicer than what it is right now. But the question is the process that we go through to get there. Let's see what can we do here. We see a mixed match of functions all thrown in. We have tangent, we have sine and cosine. We remember, perhaps if I go ahead and try to reduce the different types, maybe I get lucky. What do I have that helps me? We have one of those ratio identities that told us tangent of x is equal to sine of x over cosine of x. So let's try this. It's just we are on a trial stage. Let's see if that helps us with anything. So I say I start with the expression that I was given. I noticed there is a mismatch of stuff. So let's see if we can reduce the number of things to fewer types. Say sine of x over cosine of x. Next, I say, okay, now as far as I've gone, this is fewer type of function, but it's very hard to sell to somebody that this is really simpler than that. Maybe a tad bit. See if we can do any more. Any more means let's go ahead. The only thing I can think of right now is to take a common denominator and add them. Okay, let me correct my writing here. So I go ahead and say, let's see if you remember from algebra, how do you add two fractions? Suppose I have a over b plus c over d. What should I do? Maybe I should write it bigger. So I have a over b plus c over d. Two fractions with numerator denominators that don't seem to have much of anything to do with each other. What is the first step to do? Find the least common denominator. Is that right? BD. Then you say this one has BD as a denominator, this one just has a B, so I go and modify this by multiplying by the D. This has a D but no B, so I multiply that numerator and denominator by what? By B. No denominators are the same, and when I want to add the two fractions, I can simply say AD plus BC. Or once we are up to speed with this, if I am looking at the fraction like A over B plus C over D, I say I multiply these two, BD, cross multiply AD plus here BC, and I'm done. So we apply that idea here. I say, except that our expressions is 1 plus sine of x, and the other guy is cosine of x. So I have to cross multiply these two. Cosine of x times another cosine of x. These times that. Then this one times that one. I have to put this denominator in a parenthesis, even though this doesn't have a parenthesis itself, because if I don't, what is wrong with it? If I don't put a parenthesis here, order of operation tells me to do what? This multiply these two first. Order of operation tells you multiply these two first, then add the 1, which is totally different than multiplying these two first and then multiplying with that. Okay? So if your denominators consist of anything other than a single item, you have to put it in a parentheses, otherwise things are not going to be right. Okay, we continue. So my equation is still going. I have 1 plus sine of x times, cosine of x. Numerator, I see the emergence of something. I see a light at the end of a tunnel. I see cosine, cosine is cosine square, sine, sine, that's sine square. That tells me maybe things are settling down a little bit. So I say cosine square of x. 1 times sine is just sine of x. Sine times another sine is sine square of x. How do I know that I can do these things? That's a strength in algebra, to be quick. That's why speed is important. That's why drilling is important. You have to do a lot of drilling, and then you can see a few steps ahead of yourself and see the necessity or usefulness of doing these things. So we go to the next stage. We remember the basic Pythagorean identity. So all over here, the only identity I used was to take tangent and replace it by sine over cosine. And after that, I'm just doing algebra. But now I see another emergence of another identity. What was our basic Pythagorean identity? Yeah. So we had 3 of these things. Each of them could be written 3 different ways each. But we had some of those. So we have this plus that is 1 sine of x, 1 plus sine of x, cosine of x. Now what do I do next? This expression is same as that. Okay, this, if you wish, put it in a parenthesis. So what can I do? I can cancel them. But canceling doesn't mean that guy disappears totally. What do I write instead? When I cancel them, it becomes a 1. So don't replace it by 0. It becomes a 1 over cosine of x, which if you want, you can write it as secant of x. Now that we see this, so, well, of course, this is a lot easier to digest than that one. So it's like when the puzzle is solved, it becomes trivial. The issue is to stay on track and work your way to that. It's a style of problem solving. Okay, that was one such example. You have a lot of these things. Now, for benefit of those of you who are going to be doing certain trigonometry in your next math class, we have applications of trig identities Precalculus. Or just trig substitution. Okay, many problems that come up in science and technology and such revolve around measuring distance of two things, 2 points. Like you have a point here, you have a point here. That's one of the most basic things in science, to figure out what's the distance of these 2 points. Okay, to figure out the distance, then customarily you come across the Pythagorean triangle, and then that opens the gate to all sorts of things coming in. So the expressions that we are going to work on, things that show up typically starting from physics, then they come into calculus, then they trickle down to precalculus or trigonometry. That's the origin of these exercises. If you are wondering what's the use of what I'm doing, you will see the use in about a year or so. Here, the question is express radical 25 plus x squared as a trig function by using the following substitution. X is equal to, say, 5 tangent of theta. Assume theta is a quantity so x is some real number. For some reason it has shown up in radical 25 plus x squared. Before we even dive into it, where would such a thing show up? Well, that is an example of somebody was trying to calculate a hypotenuse. One leg was 5, the other leg was x. Okay, so somebody had a 5 and an x, and hypotenuse turned out to be radical 25 plus x squared. That's a very innocent origin of a problem. The question is, can I use trig to redo this thing in a different style? Well, here's the answer. You want to do trig, consider this to be your theta. Then x is equal to 5 times tangent of theta. That is what this one is. In your calculus class, you have to draw the picture and think about this thing all by yourself. The question is, if you do this, what happens to that hypotenuse? You have two ways of answering this. One is right off the picture, and the other one by substitution. Let's do substitution. So suppose this hypotenuse, so this is my hypotenuse. Say hypotenuse is radical 25 plus x squared. Somebody is suggesting that we change the look of it by saying 25 instead of x, put 5 tangent of theta. See if you can simplify and get something perhaps cleaner. Well, we work it out. I square it, I say 25. What is that expression when I square it? I get what? 5 squared times 10 squared of theta. What can I think of doing? Oh, these are all things, that skills that comes to you from algebra. I have a 25 and 25. That suggests something. Suggests what? Factor the 25. Okay, what does that do? 25 multiplied by this quantity in a radical it comes out as a 5. So that's again issue from college algebra. Now 1 plus tan squared. That was one of the identities labeled under Pythagorean identity. This was one. The other one, take that and divide it by cosine. So 1 plus tan squared. Remember what is that? If I divide the right hand side by cosine, what do I get? So that is secant squared. That is the. So first of all, we have to know what this identity is, and second, that actually see it ahead of time that we have some use for it here. This becomes 5 times square root of secant square of theta. Now square of secant squared, what is that? Secant of theta. We need a little bit of fine print next to this to make it actually be a legitimate operation, but I'll talk about that maybe shortly later. So what happened is, so there is room for a little bit of a talk here. We made a substitution in that expression that finally hypotenuse became 5 secant of theta. This is the kind of a process you go at the beginning of a certain calculus problems for the next step to make sense or become hopefully easier. Now, was it possible to bypass this and get the answer in a different style? Yes. If I was in this situation, this is theta. This is 5. What is the hypotenuse? This is what hypotenuse I am trying to find that. What is the connection? What formula connects these things to each other? So for example, if I say secant of theta, what is secant? Ratio of hypotenuse to adjacent. So hypotenuse is immediately 5 secant of theta. I have it. So it's bypassing that, provided that you were comfortable with that triangle, writing this definition and solving it, you get the same thing right off the bat. Now, a little bit of a side remark, just so that I wouldn't get sued for saying something that's not correct. Some issue comes up in college algebra, so this is a basic review of college algebra. What is the square root of x squared? Okay, what does it mean to say plus or minus x? When you're solving an equation, you take with a plus or minus, but radical something is one answer by definition. So the correct answer is this is absolute value of x. Okay, most common thing is to say square root of x squared is x. This is not really correct. This is a bit iffy. It's iffy with one f or two f. Is iffy. Why? My iffy is iffy. Let's see. If you are starting with a number like 7 and you square it and then take square root, this is 49, you come back to what you started. There's no problem with that here. If you started with 7, you square it and take the square root, you come back to 7, that's a confirmation of that. But suppose I had started with minus 7 and I squared it. And then I took square root. When I square it, the minus evaporates. When I take square root, try to ignore the left hand side. What's square root of 49? 7. It's not minus 7. This thing is telling you if I take the square of something, I end up exactly where I started. But that's not so. Because I started with -7, I ended up at 7. This is not what I started with. To get around that issue, what do you need to do? Say, okay, if I end up with 7, what does that have to do with what I started with? That's an absolute value of what I started with. So process of squaring, taking square roots, strips the sign off of a quantity. It strips the sign and gets the x back to you, but if it was negative, it strips the sign of it. So what does that have to do with this? Over here I had square root of secant square of theta. To be correct, I have to say this is absolute value of secant of theta. What is it that rescues me from that complication? What rescues me is this definition, which I wrote and we kind of brushed it aside. If theta is in the first or fourth quadrant, the cosine is of what flavor in that area? In the first or fourth quadrant. Cosine is positive. And so is secant. In this range, secant is positive. So when you take square root of it, when you take absolute value of it, you end up back where you were. The situation is like this. So it is legitimate to just take a square root and bypass that absolute value sign. So that is a little bit of side remark. If I ended up confusing you, just set it aside and just go with that. So what you feel comfortable from high school to do, just keep in mind there is something not quite kosher with that. So that is another example of this. So I want to go back asking you guys to do the problems of 2-1, and I still have 5 minutes to squeeze in one more identity here. Again, we are not going to have time to prove these things. So let's review what we had. We had cosine of x minus y. Let me see if you can say without looking at your notes. What was on the right-hand side? Cosine of plus sine of x sine y. And then we had the sister identity that if this is plus, everything's same, and then sine x sine y. We did a couple of examples of this. There are similar identities for sine, tangent, and sine. For tangent, it's going to be a bit different, but sine is almost same. Sine of x minus y. That happens to have sine of x cosine of y minus cosine of x sine of y. So when this is minus, this is again minus, opposite of the cosine situation, where the flavor is different from the flavor here. In cosine, you had same functions next to each other. With the sine, you have them mixed up. So be aware of all these differences. Sine of x plus y then does what you expect. Sine of x cosine y plus cosine x sine y. Now, just as last time, the simplest examples we can give for these things are find sine of 15 degrees. Well, we learned the trick. 15 is same as, say, 45 minus 30. And what this one says is that take sine of first, cosine of second, minus cosine of first, sine of the second. Hopefully by now we are up to speed with these. What was sine of 45? Radical 2 over 2. Cosine of 30. Radical 3 over 2. Cosine of 45. Radical 2 over 2. Sine of 30, 1/2. You notice something peculiar. We have seen this. Last time we saw it, what was it? It was cosine of 75. I managed to. This is the same thing we saw a few minutes ago, or in the previous lecture. It was cosine of 75. Is it accidental that they are the same, or is there something going behind the scene that they turn out to be same numbers? If this angle and that angle, what did we call them before? These are complementary angles. Co-functions of complementary angles are equal. Sine of 15 is same as cosine of 75. So complementary angle identities show their heads here. They had to really be listed under the basic identities. We had already had them in chapter 1. Like cosine of alpha is same as sine of pi half minus alpha, or 90 degrees minus alpha. Same. Sine of A is cosine of 90 degrees minus A, and so on, depending on what kind of unit you have. Tangent of beta is same as cotangent of what quantity? So trig functions come in pair, and the angles come also in pairs, complementary angle pairs. Function of one is equal to the function of the other. So let's do some maybe more advanced examples of these identities. Or just tangent of, say, x minus y. That is same as tangent of x minus tangent of y. No, it's very different from the ones that we have seen. And again, next time I'm going to show the reasoning for this. This is 1 plus tangent of x tangent of y. And similarly, tangent of x minus y, x and x plus y, is tangent of x plus tangent of y over 1 minus tangent of x tangent of y. I don't know if time's over or not, but let's just quickly do one example. What is tangent of 75 degrees? What do you think you should do? Tangent of 45 plus 30. Let me ask you to find tangent of 45 and 30 and plug it here and find out what that is. And you do need to simplify quite a bit. It's a bit of a long story to simplify and clean it up. So we are going to take a look at everything we said today with regard to these identities and their proofs. So we are still working on 2.1, kind of a lengthy section. Okay, good luck until tomorrow.